Okay, now, at this stage, we are just at the point that we can just use a method in conjugation, I should say, with the method that we had with the PSIS, Pareto smoothed importance sampling, in order to just get some kind of an assessment measures of the model that we have created. As you can see, I have, I should say, the command to install the package load. That's the thing which we have been just working with it since a couple of lectures before, and you will see that the loop package inside the package tab on my global environment RStudio is ticked, which means that the package is now ready to be used. I'm just going to go ahead and just use the function of the loop, which comes with the loop package itself. Normally, if you just want to see what kind of arguments you have to just incorporate inside the parentheses, you know, the thing which we do always, you just press F1 and you have the menu opens. The loop package comes with the RStan and RStan arm, and that's the thing which we are using. We just need as an information criteria and cross-validation done the thing which comes with the RStan arm. Okay, now the thing that it opens right now here, it's ready to just be put the things that we have in our model. You see that we have a couple of arguments from the health function that we have to just put inside the function. The first one is going to be the X, which is essentially the model that we have just created for our research, for our analysis, for anything. Right now, for the demonstration purpose, as you have been following me so far, you notice that the model that we are working with, that we just call that model A. It's one of the models that we created, which essentially it just models the Americans' women's height with respect to their weights, and it was a kind of predictive model that we said that, okay, what kind of a coefficients we can just make an inference about, that for future observation we can predict the woman's heights based on their weights which we have in our experiments. But you can have any type of the models that you have had so far from your research, as long as you have, I should say, stand GLM as a Bayesian method to just work with it. Now, it's going to be for our X. I just put the model A which I have. The other thing which I have, I just need to just put inside that model, as you will see, we have something which is called save PSIS. You know that the PSIS, that's the thing which we talked about that before. It stands for Pareto Smoothed Importance Sampling. That's the thing which we have done. We just did a kind of extensive review on that thing. And I just recommend that if you haven't just reviewed that, then please go back to the tutorials that we talked extensively about that thing. And I'm just going to put that as an OK. It seems that any weights that has been smoothed, it's going to be saved in our model then. Okay, now, I'm just going to, the model is going to be ready now. This is all the arguments that I had to just put inside this function, but you know that before we just go on to execute this line by pressing Ctrl Enter, I'm just gonna go ahead, create a name in order that in future, when I just go back to this name, I know what that object was. I'm just gonna store the model and the functions into Lou Woman. I'm just gonna execute this line by pressing Ctrl Enter, and I just get the result right now here. You see that I have a Lou Woman, which is a list of 10 objects. Okay. The things that we can have, for example, if you have the Lou Woman, you have many other things you can just write. For example, you can just go ahead, first of all, write, for example, print Lou Woman. And let's see what do we get. Okay. The things that we get, it says that this is an object of, let's say, for example, of, please listen very carefully, because this part of the Lou analysis, it's significantly important, and also as we just move on to the model comparisons, you will see that these ones are incredibly important. Okay, now look, what do we have here? You see that we just created our objects for the Lou Woman. I just printed out. I have lots of 15 different objects displayed here. The first thing is that estimate and the standard error you have. We have ELPD, Lou, and that's the thing that we talked about that exactly immediately on the previous lectures that we talked. We said that the ELPD, it's the measure, it's a theoretical measures for the predictive accuracy of the model that you have. it's a measure of the predictive accuracy of the model which you have built. And because it's a kind of a log likelihood, and essentially that's a probability that you take the log from it, then because the probability is something between 0 and 1, you expect that it's log based on the basic laws of the logarithm to produce something negative. And that's why you see that the ELPD, which also itself stands for expected log predictive density, is negative. Because essentially you're taking the log of a number which is somewhere between 0 and 1. And we assume that it's not going to be 0 because you know that the log of 0 is not defined in the whole entire math. Okay, now you will see that it is going to be minus 11.6. And now we said that it's on its own, it's a predictive measure. It's for the accuracy of the model that you have. Maybe on its own, it doesn't say anything, because you cannot say, for example, I have 4. You have to have a comparisons with that thing. Then we just, at this stage, we say that the model which we have created and the Bayesian framework for the women's heights, it's going to produce a predictive measure of its accuracy based on the measure that we have for the ELPD, which is expected log predictive density is going to be minus 11.6. It seems reasonable. We expect to have a minus number because we took the log of a number which is between 0 and 1. However, we have something as a still which is going to be meaningful. I come back to the ELP later when we just have 2 models to compare. In future, on the next tutorials, that when we are just going to have 2 models to compare based on the LU and the ELPD measures which they have, because in the future tutorial we are just going to use the LU functions in order to compare 2 models which are clustered and nested to each other in order to see which one is a better model. And over that we are just going to see that this number which is going to be the ELPD LU, it's going to be meaningful when it's going to be used as a comparison with the other model, which that model also has produced on its own a number for ELPD, expected log predictive density. Okay, however, the p-LU, but the LUs, it should not confuse us, because LU at the end of each number, it means that it is essentially a number which we extracted that and made an inference about that from the LU package. But P is essentially the effective number of the parameters in our model. How many parameters, which is, it has to be close to, I should say, it has to be close to the actual number of the parameters that we have in our model. If you remember from our model, the thing that we did, if I just want to just go back to the whiteboards that we had. If you remember from the model that we had, from the thing that we had, essentially, we saw that in the model that we created before, we said that we are just going to say that the women's height is going to be a model of the women's weight. However, we had 2 things. We had one parameter. We had, let's say, A plus B. You see that we had 2 parameters back then. One of them was essentially A, which it was the slope, and the other one was B, it was the intercepts. And you see that from the actual model that we had, we have essentially 2 parameters to just work with, and 2 parameters to just make an inference about. And we did actually, with some kind of a uncertainty as a credible interval we assigned to them. And now we see that the effective number of the parameters in our model is 3. As an integer, it's going to be regarded as 3, which is so close to the actual number of the parameters in the model that we had. And essentially, it means that this is going to be good. When you just work with some models, for example, sometimes you get the p-LU, effective number of the parameters, 30 or 40 times more than the actual parameters that you have in your system, which it means that the model has not been constructed effectively and well enough. Okay, And now the other thing that we just want, also we just come back to the other things that we just want to work. For example, the Monte Carlo, I should say standard, for example, error that we have. For example, also we have also something as the Pareto K diagnostics that we had from the, I should say, the PSIS method. You see that, for example, we have, it says that on its own, the model analysis works so fine then. Why? Because you see that, as you saw also before, when the K as a parameter shape of your Pareto distribution is somewhere between minus infinity at 5, 0.5, you have 14 parameters which they produce that effective, minimum effective number of, I should say, samples of 648, which essentially they are 14 parameters, which is a good one, which is, you see that we have effective sample size, we had 648 samples which were thrown based on those shape parameters of the Pareto, which is fitted to our model, and they produced, I should say, a good result. And you see that also we had one parameter between 0.5 and 0.7, and the minimum effective, I should say, sample size which we had for those, it was 137 samples, which is still reasonably good. And the good news is that we do not have any statistics, I should say, in terms of the counts and the minimum effective number of the samples when the things is going to be bad or the things is going to be very bad then, which is essentially, it's a good thing in our model estimates. Then we are looking into the model on its own. We do not compare that. Still, we can look at these kind of values and parameters and get an idea of how the model has been working so far. Okay, the other thing which we can do, we can just go ahead. You see that we have the Lou women. The thing which we have, you see that when you just put the dollar sign, you have a range of this stuff. For example, you have all the things that you just wanted to just work with. For example, you have your estimates, you have your point-wise, you have your diagnostics, you have the objects, you have, let's say, for example, these, I should say, ELPD, which is expected log, probability, I should say, density. You can extract many other things if you want. You see that it's going to be 15 in total, and you have the access to them here. And also the other thing which you can do is that you can have a plot. Let's see if we can just plot these items that we have. Let's see what do we get. Okay. And as a final thing for this tutorial, I just wanted to just show a plot for you of the Lou object which we created. You see that on, let's say, the x-axis, we have still 15 as an index of the data point, which essentially there are the number of the K parameters, which is the shape parameters of your Pareto, which you fitted into, I should say, the top 20% of the highest, I should say, of the sample ratios at the tail of your importance weights. When you just had the distribution of them, you see that we had 15, which I should say 14 of them. They were somewhere, I should say, between, I should say, less than some minus, a little lower than 0, and all the way go to 0.5. This region, that was the thing that we said that it's going to be very good. And we had also one parameter, the shape parameter of your Pareto distribution, I should say, which produced an effective sample size, I should say, then it was at this region, which is going to be still good. And we had some sample size related to that, which effectively it shows that this model, even when you look at that individually without compared to the other model, this is still good because we have still with these, I should say, shape, I should say, parameters of your Pareto distribution, which you fitted into, I should say, your sample, I should say your weights, importance weights, still you had enough and reasonable sample weights for your model then. Okay. And now this is the plot, which we have seen that plot also before. And now at this stage, I hope that you understood that how to use the Lou method, at least to get some kind of understanding of how your model works. On the next tutorial, when we come back, we are just going to use these Lou functions and package in order to compare between some models which they can be also regarded as a nested model into each other. Then we have done that in the non-Bayesian context. Now we come back with the Bayesian framework to see how it works.